Hello and welcome back to Siblings in Science. I'm Bradley.
And I'm Joseph.
So, Joseph, what's the topic for today?
Well, today, Bradley, we are going to be talking about temperature and specifically some are called statistical mechanical temperature because there are actually quite a lot of different definitions of temperature.
So, it's a really sunny day today, and I think it's about 26 degrees here. Is that the kind of
Yeah.
temperature that we're going to be talking about?
Yeah, exactly. So the temperature you get outside, but like we're UK based, so you said degrees Celsius there, so you said 24 degrees, I think.
Yeah.
So in physics, we don't actually use degrees Celsius. We use the number you said, add 273.15. So we're going to be about like 290 degree Kelvin, as we call it.
And why do you use Kelvin in physics instead of degrees Celsius?
Good question. That's because Kelvin. So zero temperature. Do you know what 0 degrees Celsius? Do you know what that measuring point is?
Uh,
So
well,
what
anything
happens at
below
zero?
that is when it starts to freeze.
Exactly. Yeah. Exactly. So 0 degrees Celsius is freezing point,
Yeah.
and then zero. So that's based on water. So water, you take 0 degree Celsius
Yeah.
as one of the fixed points, and then the other fixed point you take 100 degrees Celsius,
Yeah.
which is the boiling point of water.
Mm.
In physics, we don't do that. We say 0 degrees Kelvin is absolute zero. So it's weird that temperature, it has an absolute zero. So at that zero, nothing, like you can't get colder than that zero.
Okay.
And then the other boiling point is we get talk about the tricritical point of water.
And is that
That's
100
when you get
degrees Celsius or?
um no, it's not. It's actually, if I get this right, I think it's close to 0 degrees Celsius. So it's about no is it so it's about yeah, so 0 degrees Celsius is 0.15, I think, degrees Celsius. Again, we don't have notes here, so this is off the top of my head. So it's not about 0.15 degrees Celsius, and it's the point where you can have liquid, gas, and water
Hmm.
all in the same state. So that's what we mean by the critical point of water.
Hmm.
So you may wonder, like, it's a bit unusual you not being able to get to zero, because surely zero, like we can get to 0 Celsius, and that seems quite reasonable. But if I was, and we like, let's go to an analogy of velocity. We can go to zero velocity, like we can not move. So do you understand this?
Yeah.
Okay, so we can get to zero velocity and we can not move. And it seems then a bit odd that we can't get to zero temperature.
Right. And what?
Now, the reason for that is we're thinking of it the wrong way up. So,
So we're thinking of it wrong in terms of degrees Celsius.
no, well, so degrees Celsius is wrong anyway, because we want to be working in degrees Kelvin.
Okay. Okay.
But yeah, so we're not we're wrong. We are wrong in thinking of about it in terms of degrees Kelvin. So in physics, what we define is not temperature, but 1 over temperature. So do you know what 1 over 0 is?
0.
No.
Oh, it's incorrect. It's not.
Well,
You
okay,
can't
yeah. So
divide by 0.
no, yeah. Technically, I think you were saying the right thing. It's not really well defined.
Yeah.
So, but being a physicist, we ignore that and we say it's infinity.
Hmm.
And if I told you we can't get to infinite temperature, that wouldn't surprise you, would it?
No.
So this is what. So that we think of temperature the wrong way up as it should be. We should be thinking of zero temperature actually is something that's infinite.
Ah. Okay. Okay.
So that's why we can't get to zero temperature.
Yeah. Got you.
Okay. So that brings us to the question of how we define temperature.
Right.
So, do you want to give me like a rough definition? What you think temperature is?
Temperature is based upon how hot or cold it is. It's a very basic definition of
Well, yeah,
temperature.
so it gives some sort of measure of how hot or how cold it is, but then you need to define what we mean by hot and cold,
Mm.
and that's tricky without the use in temperature. So there are a number of definitions of temperature. There are ones that define it using gases. So you have, if you heat up a gas, it gets bigger,
Yeah.
and the rate at which it gets bigger is what we call temperature, or is related to temperature. That's called the ideal gas temperature, or the gas temperature. But what I said at the beginning is I want to look at something called the statistical mechanical temperature.
Okay.
Now, all these temperatures, they turn out to be equivalent, but the way they're defined is different. So, even though I'm going to define temperature or talking about temperature in one specific way, it corresponds to the temperature that, like, we have normally.
Got you.
Okay, so I mean, you can imagine 100 boxes.
Mm-hmm. Boxes of beer.
Well, okay, well, you've used the analogy, so let's use boxes of beer.
Okay.
Why not? And okay, we'll have. Can you name? Let's call it. Let's have ale and lager.
Yeah.
I guess.
Oh my God! You know
So
the
you
difference
have-
of beers. That's amazing.
I was going to name some brands, but I can't remember brands.
No,
Okay,
probably
so
best.
we have. Yes, well, can we have 100 boxes? And let's say each of those boxes can have a certain number of ales and a certain number of lagers in it.
Yeah.
And let's say these correspond roughly to a state. So if the box has 5 ales in it and 7 lagers, we say it's in state 5-7, for example.
Yeah.
Okay, so what would a state with 2 lagers and 3 ales be in?
2, 3.
Exactly. So we label the states like that. And with each of those states, we are going to give it a quantity, which we're going to call energy.
Mm.
So let's say an ale has an energy of 1, and then a lager has an energy of 2.
Mm-hmm.
So the state 1, 2 would have 1, an energy of 1 plus 2 times by 2, because you times them by 2, because I said lager has 2 things.
Yeah.
And that would give us an energy of 5.
Yeah.
Now, you're going to take those 100 boxes, and you're going to ask, what is the probability that, or what fraction of those boxes are in the state 1, 3, for example? So 1 ale, 3 lagers.
Mm.
And there's some way you want to quantify this. You want to give this a number. You want to find that probability.
Mm.
So do you understand roughly what we're trying to do?
Yeah.
Okay, do you want to try and explain back to me?
Lagers are better than ales because lagers give you more energy.
Well, we need to check that. I don't actually know that. But yeah, okay. So I will take that as, yes, I do know, but I don't want to explain it back to you.
Yes.
So,
Oh, I don't know, but I'm pretending I do.
okay. So, yeah. Whatever. People have the option to rewind this if they want it. Okay, so we have these boxes. We have them. Each box is in a different state. That's determined by the number of ales and the number of lagers in each box.
Yeah.
With each ale and with each lager, we associate an energy. So each box has an energy which is determined by the number of ales and the number of lagers
Okay.
in that box.
Yeah. Yeah.
And what we want to do is we want to find the probability, or we want to find the fraction of those 100 boxes. How many of those 100 boxes have like one ale in it
Right.
and 3 lagers in it?
Okay.
Okay. And the way this works is this is related. This is determined by one quantity only.
Mm.
And this quantity is, we call it beta. So the Greek letter beta. And without going into the maths of what this is, the smaller beta is means the more uniform the distribution is, or the more varied things. So it means that the probability of having a box with one ale and one lager is the same as the probability of having a box with 7 ales and 100 lagers.
Yeah. Okay.
So that's if you have a small beta.
Yeah.
If you have a large beta, that it massively favors boxes with small energies.
Okay.
So the box with no ales and no lagers will dominate the number of boxes. So out of your 100 boxes, like 99 will have like no ales and no lagers.
Yeah.
Because that's the lowest energy.
Yeah.
Okay. So, and if you have a medium energy, you always tend to have lower energy stuff more predominantly, but the higher the energy, or okay, let's rephrase that in terms of beta. I was jumping ahead of myself. Oh no, okay, I'm confused myself now. Yeah, so you're always predominantly going to get lower energy things, but if you decrease beta, then you are going to get more high energy stuff in there as well.
Okay. And how does that relate to temperature?
Exactly. So beta, this quantity which determines the number of states, is exactly equivalent to 1 over the temperature.
Right.
Spare a constant of proportionality, which no one cares about.
Mm.
So that is that's what we mean by temperature. It gives you a measure of how distributed the system is.
Okay. Yeah.
So if we had a box, this is hard to get your head around. If we take the room you're in now,
Yeah.
if we knew exactly where every one of those particles is, then technically the temperature of that room is 0.
Right. Okay.
So it's a weird thing to notice. It's not technically true because you let it equilibrate to thermal equilibrium. But I think that is probably enough.
Mm.
Should we stop there?
Yeah.
I need to work out how to turn this off. Okay. So do you want to
I feel
tell them about our stuff? Like,
so. You're saying that in terms of temperature, that Kelvin is a better measurement of temperature than degrees Celsius, and
Yep.
you were also saying that the way we're looking at temperature isn't necessarily the right way
yeah.
because it's determined by the energy
Well, that's one way of
that's
looking
given
at it.
off, and the betas associated with that.
Yeah, so that's roughly right. So what I'm saying we should be looking at 1 over temperature, which is equal to beta. That's more fundamental in physics. And then the energy, the beta is related to the probability of being in a given state.
Well, and that is something to take away with us on a nice sunny day. I will now have a big box of ales and another big box of lager, just because I feel like it. Thanks for listening. We are Siblings of Science. Follow us at Siblings and Sci. Joseph, do you want to end with a physics fact?
Oh yeah, I haven't prepared one.
No.
Dum. Let me rack my brain. Okay, not a physics fact. Somebody can look up. Look up Ken Wilson.
Okay.
He's a very unknown physicist. He died quite recently, well, 2013. But look up him and see what he did. It's not a fact, but it's something related to physics.
Great. Lovely. Well, see you all next week. Bye.